Developers today are deeply integrated with AI assistants in their local environments. It's natural to want to point these highly capable agents at a live website and ask a simple question: is this secure? The problem lies in how security testing actually works. Traditional scanners operate through relentless aggression. They crawl every hidden link, fuzz endpoints with garbage inputs, and inject payloads to break them. Hand an unrestricted AI control over these tools, and you invite disaster onto your live infrastructure. A hallucination or a poorly looped command could easily lead to swamping a server into a denial of service or permanently corrupting a live production database. We are left with a paradox of interaction. We want the AI's analytical power to comprehensively map out our security flaws, but we cannot allow it to actively touch the live system to get that data. A developer named Venkat built a solution to this exact problem. He created the safe-web-audit server, an open-source tool designed specifically to resolve this aggression paradox. The architecture relies on the Model Context Protocol, or MCP. Think of MCP as a highly secure, standardized bridge that tethers an AI to external tools. It dictates exactly what the AI can see and do, enforcing strict rules on passing data. Venkat built this specific protocol integration with a philosophy he calls defensive by construction. The entire value of the tool lies in the actions it mathematically refuses to execute. Reliable safety with intelligent agents is achieved by engineering environments with hard-coded physical boundaries that the AI simply cannot cross, regardless of the prompt received. Let's look at this flowchart to see how these constraints work in practice. First, the tool prevents crawling by using a single head request. It only asks for the topmost layer of metadata, things like security headers, and discards the heavy response bodies entirely. If a website tries to bounce the request to a new address, the protocol treats every single redirect as a hard checkpoint. It refuses to blindly follow links, forcing a strict reevaluation of the safety rules at every hop. It also features strict server-side request forgery protection. By explicitly blocking the tool from resolving private or internal IP ranges, the AI hits an impermeable red barrier if it tries to map out your hidden backend networks. Before any data is handed back to the AI, it passes through safe evidence mode. The tool actively scrubs sensitive information, erasing session cookies, emails, and IP addresses from the headers to ensure no private tokens leak to the language model. Before any of this begins, the tool demands consent. It refuses to execute an audit unless the user proves ownership, either by placing a specific DNS record or uploading a verification text file to the server. By stacking these 5 constraints, the architecture neutralizes the unpredictability of the language model. It takes an agent capable of wreaking havoc and carefully confines it into a provably safe, verifiable auditor. The result is delivered straight to the developer's local machine, a clean, thoroughly redacted snapshot detailing the site's HTTPS posture and mapping out exactly which security headers are missing. With this risk-free context, the AI can then do what it does best. It reads the findings and generates highly specific, ready-to-paste configuration fixes for web servers like Nginx or Apache, all without ever executing a single line of code. This workflow proves that complex, high-stakes security diagnoses do not require active testing. They can be resolved passively, efficiently, and entirely locally, keeping live infrastructure completely insulated from automated experimentation. The Safe Web Audit Server solves a specific problem for website administrators, but its underlying architecture carries broader implications for the way we integrate artificial intelligence into the software industry. Meaningful progress in these automated workflows depends on engineering smarter, consent-based limitations that prevent models from gaining unchecked access to live infrastructure. Venkat's architecture demonstrates a precise method for balancing automation with human consent. In a landscape of expansive technical capability, the reliability of a system is defined by the strictness of the boundaries it cannot cross.